Okay, so we're going to be talking about natural selection today, and natural selection, like evolution, is one of those things where there's a semantic piece that gets really tricky for people. And we talked about this a little bit the other day, that when we're talking about evolution, in science, we mean one thing, and we mean something really specific. So in science, when we talk about evolution, we're talking about a change in allele frequencies. But outside of science, people talk about all sorts of stuff and call it evolution. A lot of people outside of science think of evolution as how life began to begin with. So, how did life get here? Some people say, well, evolution explains that, and this doesn't. A change in allele frequencies doesn't explain how life got here. Some people say, and I'm going to put this in quotation marks because this isn't what scientists think or say at all, but a lot of people outside of science will say monkeys turning into humans. And some people say that, and they actually think that that's something that could have happened. Other people say that, and they don't believe that is what happened. But either way, this is something that you hear about, but that's not really, in science, when we talk about evolution, we're just talking about a change in allele frequencies. It's really different. The thing about a change in allele frequencies is that this is observable. We can see it. We see allele frequencies change in populations all the time. And we give it a word. It's called evolution. That means that this piece right here, the idea that changes in allele frequencies can happen, and we call that evolution, that means that this is true by definition. If we look at something and we give it a name, then you can't say, well, it doesn't happen, because we saw it happen. Where people get into arguments about evolution is sometimes if one person is talking about a change in allele frequencies and somebody else is talking about monkeys turning into humans, then there's some room to say, well, I'm not sure that happened. So one of the things that we need to do in this class is pin down our definitions. When I say evolution, this is what I'm talking about. It's something that's true by definition. And we have the same kind of problem with natural selection. Most people, when they say natural selection, they're not thinking about the idea that evolution is a change in gene frequencies, and there's a variety of ways that it can happen. But in science, that's exactly what natural selection is. Natural selection is one way that evolution can occur, and by evolution I mean a change in allele frequencies. So in science, we call natural selection a mechanism for evolution. And this is something that we have observed. So we know natural selection happens because we have seen it unfold. We have evidence that natural selection occurs. But again, outside of science, it gets tricky, because outside of science, what most people think about when they think about natural selection is, well, first of all, they think it's the same as evolution. They think it's just the same thing. What's the difference between natural selection and evolution? Most people outside of this context would say, well, there's really not. They're the same thing. And in particular, what most people think about with natural selection is this idea of improving species and creating new ones. And what we'll see is neither one of these things is really accurate at all. This is not incorporated in our definition of natural selection. Where these things come from is that if you take natural selection and and think about how it can cause evolution. And then we imagine, well, what would happen if that went on for a really, really long time? Then like our series of pictures, where there's these incremental changes that add up to big changes, we now have a theoretical framework upon which we can say, well, if these things happen at a certain rate for a really, really long period of time, then we can explain things like the similarity between humans and other primates. And we can explain things like how one species might evolve from a population of a different species over a really long period of time. So these definitions and observations can explain things that we see in the world, and we can use those to make predictions. So that's ultimately where we're going to go. And I mentioned to you that that when we talk about evolution, my goal for you is to put something together that's going to be real similar for what I asked you to do for genetics. So with genetics, I told you what I wanted you to do was be prepared to teach this stuff. And so what I had you do was work through some problems, and then I had you like make a slideshow with all your evidence in it, and then I very specifically said, okay, now teach me how you used a Punnett square. That's what you did. You made a recording of yourself explaining your Punnett square, just like you were teaching it. And with evolution and evolutionary theory, we're going to do something real similar, only your goal is not going to be to teach it. Instead, what I'm going to ask you to do is tell me a scientifically accurate story of how evolution could occur through natural selection in a population of organisms in an environment such that we get new adaptations, which we haven't talked about yet, and eventually we get speciation, which we haven't talked about yet. So I'm going to ask you to put together a story that is backed up by scientific explanations and evidence of how it is that we could imagine a new species forming where it hadn't been in existence previously. So for today, the big focus is this idea of natural selection. So natural selection is a mechanism, it's a way that evolution can occur, but it's not the same as evolution. So one of the things that we're going to try to focus on is how does natural selection tie into evolution? It's not the same thing, but it's clearly related. And just as a reminder, if you wrote this down the other day, then you don't have to write it down again. But when we talk about evolution, we're talking about a change in allele frequencies. And when we talk about allele frequencies, we're talking about the percentage of chromosomes in a population of organisms that has a certain allele. So in this class, we're going to largely look at organisms that are diploid. They have pairs of chromosomes like humans and mice and trees and stuff like that. So in that case, every organism has 2 chromosomes that have the same gene on them. So every individual represents 2 possible alleles. And so let's say we were looking at mice. If we looked at a population of 50 mice, that's 100 chromosomes per gene. And that means that there would be 100 alleles in that population, right? Every mouse would have 2 different alleles. They might be the same, but they would have alleles on 2 different chromosomes. And let's say that there was an allele that caused the mouse to have a little purple spot on the tip of its nose. So it's the purple nose gene. And if they have the allele that causes the purple tip, they'll have a purple tip on their nose. If they don't, then they won't have the purple tip on their nose. And let's say that out of those 100 chromosomes, 37 of them have the purple tip allele. If that number changes over time, if it becomes more common, then evolution has occurred. If that number becomes less common over time, then evolution has occurred. And one of the things that we are going to start thinking about today that is new, that we haven't talked about, is that can only happen when there are births and deaths in a population. New organisms have to be born, and existing organisms will eventually die, and that's the only way we can change allele frequencies. If we look at our population of mice, 50 mice, there's 37 of those alleles that cause the purple nose tip. If we look at those mice and no new mice are born and none of our existing mice die, then none of their chromosomes are going to change, which means the allele frequency won't change. The only way we could have a change in allele frequencies is if, for example, two mice that happen to have the purple tip allele have a baby mouse. And maybe that baby mouse has the purple tip allele from both parents. That means that the allele frequency will have gone up because that mouse has 100% of its chromosomes with the purple tip allele. So we went from 37 to something higher. If then one of the original mice dies, then we're losing that 50% allele frequency, and our allele frequency will drop a little bit. And it's a little complicated. The math gets a little complicated because diploid organisms can have 0, 1, or 2 alleles. They pass one of those alleles onto their offspring, which means just because an organism is born doesn't mean an allele frequency has to change, but it could. And mathematically, on average, it turns out that we can make predictions about this based on what I'm about to explain to you with natural selection. Okay, so we are taking a bunch of probability and statistical stuff and kind of putting it all together, and I'm not going to go into the mathematical details, okay, except to say that we'll get changes in allele frequency with births and deaths of organisms. That's the only way we can do it. Individual organisms can't evolve. So whatever allele frequencies any one individual has is what they are going to keep. They don't change over time. When we talk about natural selection, we have to think about a related concept called biological fitness. And biological fitness is pretty straightforward. Basically, what biological fitness does is it describes how likely any one particular organism is to survive in a particular environment. And we actually, biologists give it a number. It's usually measured on a relative scale. So a high number close to 1 means they're very likely to survive. A low number close to 0 means they're less likely to survive. And it's all based on probability. So there's no guarantee of it happening, but you can imagine in this image, for example, you probably can't even see right off the bat that there are 2 moths here. There's one light-colored one on the right and one dark-colored one on the left. In this particular environment, we can all see the light-colored moth is much less likely to survive if there are any kind of predators. And that's usually what camouflage is about, right? Camouflage is about hiding from predators or hiding from your own prey so that your own prey doesn't run away. And moths aren't typically known as fierce predators, so probably what's going on with these critters is that they get eaten by birds or something. And you can imagine that a dark-colored moth in this environment is a lot less likely to get eaten, which means it's a lot more likely to survive, which means its biological fitness is higher. When an organism is more biologically fit and it lives longer, then again, this is kind of rolling some statistics in there, but they will, on average, have more offspring. So one of the things that happens is when biological fitness is greater, organisms that have that fitness are likely to have more offspring. It's not a guarantee. It's possible that this dark-colored moth is going to fly off the tree, get eaten by a bird, and the light-colored moth is going to live for another 5 years and reproduce once or twice a year. We don't know for sure, but on average we can say it's more likely that dark-colored moths will have more offspring that survive than light-colored moths. Okay. Biological fitness is related to a couple different things. One of them is the environment. So one of the things that we need to think about is that we can't just say this organism is better than this one. We can't say this individual is better than this one. We can't say this group of organisms is better than this one. The only thing we can say is in any one particular environment, certain individuals are more likely to survive. So an organism's fitness depends on the environment And you can imagine that environments change. So if we were to think about this polar bear, for example, this is a pretty good set of characteristics for an organism to have when it's really, really cold. And when it's really, really cold, then there's lots of snow and ice, so it's got some nice camouflage. When it's really, really cold, they would need lots of fur and thick layers of fat to stay warm. When it's really, really cold, being a fierce hunter is good because you're not going to have a lot of small critters. Like, you don't have a lot of small bugs and small mammals. You have like seals and polar bears, big things that can survive the cold weather. But we could imagine that environment could change. And if environment changes, then fitness is going to change as well. If we were to take this polar bear and put it in a tropical forest, its fitness would plunge. Or if we were to look at a gradually changing climate that changes over a really long period of time, such that it's not so cold anymore, then polar bears that look like this are going to be too hot, and they're not going to be camouflaged anymore. So as environment changes, fitness can change too. And if we think about long periods of time, it's guaranteed. Over long periods of time on this planet, nothing stays the same. Nowhere on Earth looks exactly the same now, it feels exactly the same now as it did 1 million years ago. So change is guaranteed, which means the ability to kind of make adjustments so that your fitness matches your environment will be a real benefit to organisms that can do that. And as it turns out, that can happen if we have one condition met, all right? So we've already talked about how organisms in a population are more likely to survive and reproduce if they're more biologically fit. Something about them allows them to survive more and or reproduce more. Natural selection explains that if that's because of genetics, in other words, if their alleles are responsible for their increased fitness, then when they reproduce, their offspring are likely to inherit at least some of those alleles. And again, this is a statistical thing because it's possible that two very biologically fit parents could have offspring that's not very biologically fit. You can imagine that two light-colored mice in this light-colored environment might have a dark-colored baby. It happens. But on average, organisms that have alleles that increase their fitness are likely to have offspring that have at least some of those same alleles. And if those organisms are reproducing more because they're surviving longer, then what we'll see is that over a period of time, organisms will start to have more and more and more of those alleles in the population. And that's what we call natural selection. It has to do with what we call differential reproduction. If differential reproduction is caused by biological fitness, and it's genetic in nature, then we have what's called natural selection. And that's a change in allele frequencies, which means natural selection results in evolution. So natural selection isn't the same thing as evolution. Evolution is a change in allele frequencies. Natural selection is this idea that biologically fit organisms are more likely to reproduce. If their fitness has to do with their alleles, then their offspring are more likely to have those alleles as well. And that is going to gradually change the fitness of the whole population by gradually changing allele frequencies for the whole population. In other words, natural selection is one way that evolution can occur. There are other ways as well. Natural selection is one, where you have organisms with beneficial alleles that survive and reproduce more, and then they pass those alleles on to their offspring. This set of images, by the way, is taken in the desert southwest of the United States. These are the desert pocket mice. And one of the things that makes this particular population of organisms so interesting is they live side by side. there's places where there have been these rocks, intrusions, like volcanic rock, that are right next to sandstone or sedimentary rock, and the coloration of the rocks is dramatically different. So as a result, there's this constant natural selection going on. Mice that live in the darker areas are more biologically fit if they're darker colored. Mice that live in the lighter areas are more biologically fit if they have lighter colors. But these areas are right next to each other. So there's constant migration. We have dark mice that move onto light colored rock and light mice that move onto dark colored rock. And there's interbreeding as well. So they're part of the same population. They have the same genes, they're the same species, but you get these real distinct colors, and there is constant natural selection going on. Every time one of the mice moves away from the background that camouflages it the most, it is instantly more likely to get eaten and less likely to reproduce and pass on its alleles. In order for natural selection to occur, we have to have a couple of things, key ingredients for natural selection. The first is, since natural selection causes evolution, which is a change in allele frequencies, we have to start with some different alleles. So natural selection requires variation. It requires different alleles that cause some individuals in a population to be more fit or less fit than others. And you can imagine if that weren't the case, if we go back to our theoretical population of purple-nosed mice, if every single mouse had 2 purple-nosed alleles, and every single mouse had a purple nose, then there could never be a change in allele frequency. Every time mice reproduced, their offspring would have 2 purple-nosed alleles, and the resulting offspring would have purple noses. That trait would not contribute at all to the fitness of any of the mice in the population. So we need to start with variation. Things need to look or behave differently because of their alleles. And then the other piece that we need to have is an environment in which some of those alleles are more beneficial than others. And that's where you get some interesting stuff, because that can change. So we call that environmental piece selection pressure. Selection pressure is when the environment makes it so that certain alleles are beneficial and certain alleles are not so beneficial. And when you get a wide variety of different alleles in a potentially varied or changing environment, then there's selection pressure to have a lot of different appearances in a population. This population of mussels might very well all live in the same spot. The different gradation of their shells might have to do with where they are in the intertidal zone, the kinds of rocks that they end up living on. These alleles are going to be in the population as a whole that cause these different coloration patterns, and it might be that there's no one set of alleles that is the best in that population. So there might not be any overall selection pressure. Whereas if there were an environmental change, like if there was a big sandstorm and the beach and all the rocks got covered with light-colored sand, and the only areas left were areas that were real light-colored like this, then all of a sudden these mussels would be more camouflaged, and there would be tremendous selection pressure. The rest of the mussels would be a lot less likely to survive, and they would be a lot less likely to reproduce as a result. So we've got to have variation, we've got to have selection pressure. And I mentioned that I want to make sure that we know what natural selection really isn't about, because there's a lot of misconceptions. One thing that a lot of people think is that, well, evolution is this process that leads towards perfection. It's this endless tinkering that leads to a perfect specimen when it's done. And that doesn't happen. It's not all powerful. It can't produce perfection for a couple of reasons. One is there's a moving target for perfection, right? As the environment changes, what worked well in one environment may not work so well in another. The other thing is that natural selection can only work with alleles that are already in the population. So So if we have a population of organisms like humans, and we have knees that are pretty nifty, but not indestructible, then you know what would really be great is if natural selection suddenly started creating indestructible titanium knees that never broke and never wore out and never hurt and could like sustain incredible force and pressure. But that's not going to happen because those alleles aren't there to begin with. Okay, what we can say is in natural populations, organisms with sturdier knees are going to have an advantage over organisms whose knees give out. But we can't say that natural selection is going to create alleles from nothing. It has to work with the alleles that are in the population to begin with. And the other piece is, a lot of times people will talk about evolution as if it's trying to do something. Evolution is trying to make certain organisms stronger, or trying to make a certain organism toxic, or trying to make a certain organism more energy efficient, but it's not trying to do anything. Natural selection isn't a conscious process. There's no sentience, there's no thought. It just happens. It happens to be that organisms with beneficial alleles in a certain area will reproduce more. A larger percentage of the population over time is likely to have those alleles. That's natural selection. It's really straightforward. And there is no guidance of that. Okay? And the last thing that I want to mention is this is where we start moving from observations and definitions to things that are more interesting and also less certain. So if we start with this idea that we've already established, that natural selection will cause beneficial alleles to become more abundant in a population over time, and then we acknowledge that that is one way in which evolution can occur. So natural selection is a mechanism for evolution. Then, over long periods of time, we can imagine, just like our picture of a person aging one day in every picture over 15 years leads to noticeable changes. We can imagine that given reasonably long periods of time, particularly in a changing environment, we might see some major changes, perhaps even new species. And we can see natural selection happening over the short term. We can and we do see it. The peppered moth is a really good example of that. We talked about that last week. You saw real pictures of them just a few minutes ago. These are drawings, but what happened was there was an environment that was dominated by light-colored trees. In that environment, the light-colored moths were more abundant. When the Industrial Revolution started and trees started getting covered with soot from coal, then the dark-colored moths became more abundant because they were more camouflaged, so their alleles became more common. And then in areas where they've cleaned up some of the air pollution, it's reverted, and now we're starting to see more of these light-colored moths as well. We can observe that. We've seen those changes happen over the last 250 years or so. We know that it has to do with alleles, so we know that natural selection can occur. But this is a very different proposition from saying, okay, well that's a new species, because it's not. Same species of moth, the alleles are still in the population, we're just seeing changes in the relative amounts of them. So we know we can see natural selection. We know that causes a change in allele frequencies. That is defined as evolution. So we know natural selection causes evolution. And then the big things that we'll dive into starting next week is this idea of, well, could we maybe get a new species from something like this? Right? So the next task for all of you is to work on an assignment that's on Canvas. And it's called the Peppered Moth Activity, and what we need is some data. So in just a few minutes, I'm going to have you all collect some data so that we can take a look at what kind of trends we see statistically over a relatively short period of time.